In this screencast, I'm going to derive the thrust equation. So we start off by looking at a very simple expression for Fr, which is the thrust on the rocket as a consequence of expelling mass at a rate m dot at a velocity which is given here as Ve. But Ve is the effective exhaust velocity, so it's the term that we often see in the simple rocket equation, and it's a simplifying term. It's not the actual exhaust velocity, but it's the velocity value that we would have to use in order to obtain the measured thrust when we use the measured mass flow rate. The true exhaust velocity is different, and that's because we have to include the effects of not just the reaction of the rocket to the mass being expelled, but we also have to include the effects of ambient pressure, the finite area of the nozzle, and the pressure of the exhaust gas as it crosses the exit plane of the nozzle. So PE is the pressure of the gas at the exit plane, AE is the area of the exit plane, and PA is the ambient pressure surrounding the vehicle. So what we're going to consider first of all is the situation when we have a closed combustion chamber. So here you can see the nozzle has a wall or a cap over the end. We've got gas in the combustion chamber, so these blue arrows, and that gas is exerting a force because of the fact that it's generating a pressure inside the chamber. And then on the outside we have atmospheric pressure, these green arrows, and that pressure is exerting a force also on the structure. It doesn't matter whether we think about the combustion chamber pressure or the atmospheric pressure. In either case, the forces are balanced because this nozzle is closed. So you can see that for each newton of force in one direction, there's an opposing newton of force being exerted at the opposite side of the system, and likewise with the atmospheric pressure. So that's a nice simple system of balanced forces, but in a rocket we have unbalanced forces, and it's that imbalance that creates the net thrust and the motion of the vehicle. So let's consider next the force which the chamber walls exert on the combustion products, in other words the gas within the combustion chamber. So the chamber walls act on the gas, and there's a force on the gas as a consequence, and that force, which we'll call Fg, is given by the surface integral of P dA. In other words, the pressure multiplied by an area element dA integrated over the complete surface area of the combustion chamber and the nozzles. So this looks like a very simple expression, and it is conceptually simple, but you can see that it could be quite tricky to evaluate in practice, because in practice these rocket designs, these combustion chambers, can have very complicated shapes. There are converging and diverging surfaces. So this isn't trivial to evaluate. More importantly, we have to remember that in reality that nozzle isn't closed. So the question is, what happens when we allow that nozzle to be open? What happens to a volume of gas as it passes down the combustion chamber and through the nozzle? So let's look at that. So this is what we call a control volume. So it's a small element of gas which we imagine that we're tracking down through the system. So the interior surface of the gas feels a force which is given by the pressure, which in this case is just the pressure in the combustion chamber, multiplied by the area of that cross-sectional nozzle at the position that we're evaluating the gas element. On the opposite side, so a little bit further along across the thickness of that gas element, there is a pressure gradient. So the pressure on this side is actually lower. So the pressure is P, the interior pressure, minus dP, the drop in pressure across the element. And if we consider this to be an infinitesimally thin element, then we can evaluate the area as A. We can track that all the way to the exit plane, and at the exit plane we see that we can actually give a value to the pressure. So the pressure at the exit plane is PE, and the area at the exit plane is AE. So if we think about the way that the forces are acting on that gas volume, we can see that in fact the force on the gas is modified by a retarding force, which is this PE AE term. So that's simply recognizing the fact that when we open the nozzle, the gas feels a lower pressure on the exterior surface of the slab, and that pressure leads to a lower force, which is given by PE AE. So the force on the gas then becomes the integral of P dA, so the integral of pressure times area over the entire surface area of the structure, minus this retarding force PE AE. We also know that the force on the gas leads to the expulsion of mass, and therefore by appealing to conservation of momentum, we can see that Fg is also equal to the mass flow rate multiplied by the true exhaust velocity, so the velocity at which this slab is exiting the plane. Now let's think about the force on the rocket exerted by the gas. Again, that force can be written very simply as the integral of P dA evaluated over the entire surface area of the structure. But again, we have to consider what the open nozzle does to the dynamics of the system. And to do that, we have to consider an unfiring motor. So considering the unfiring motor helps us to understand the nature of the forces which are being built up on the system from the ambient atmosphere. So here is an unfiring motor. There's nothing going on in the combustion chamber. The green arrows represent atmospheric pressure bearing down on the system. And if we have that motor sitting on a test bench or on a launch pad, we don't expect the motor to move. It's unfiring, there's no motion. So that tells us that if we draw a plane that cuts the motor, we can draw that plane such that it cuts at any orientation at any point, and because the motor isn't moving, we know that the forces on one side of that plane must balance the forces on the other side of the plane. So in this case, the forces on this side of the blue dotted line must be equal and opposite in magnitude to the forces on the other side of the line. If I move that, so the forces on the top half of the motor balance the forces on the bottom half of the motor. The forces to the left of the line balance the forces to the right of the line. That might seem trivial, but if we consider that plane now being moved to the exit plane of the motor, we discover something quite interesting, which is that at the exit plane, the forces on the left of the motor are balanced by the force on the right of the line. And the forces on the right of that line are easy to evaluate. It's just the ambient atmospheric pressure multiplied by the cross-sectional area of the exhaust exit plane. So with the unfiring motor, those forces balance. But now what we have to do is consider what happens when the motor is firing. So when the motor fires, the exhaust gas leaves the nozzle at supersonic as a supersonic flow. And hydrostatic effects, in other words, the effects that the flow would see from the ambient atmosphere, only travel at the speed of sound. So what that means is that when the motor is firing, these hydrostatic effects are no longer felt by the motor. And that tells us that this side of the balance disappears. And so when the motor is firing, the motor feels a retarding force because these sources of pressure are still present. So we still have a retarding force which is equal in magnitude to the area of the exit plane multiplied by the ambient atmospheric pressure. And so when we look at our expression for the forces on the rocket, we find that they're modified. So it still includes the surface integral of P dA, but it includes a retarding force, which is the force of the atmospheric pressure multiplied by the area of that of that exit plane. So now we have an expression for the thrust on the rocket, and we have an expression for the force felt by the gas. And those two expressions both contain the same surface integral, and that turns out to be very useful. The term that we're really interested in is this one. What we want to do is develop an expression for the force on the rocket, in other words, the thrust of the rocket. But we can use the fact that we have an identical surface integral here and the fact that we know that this gas force can also be written as m dot ue. So I can first of all take this expression, so I can take the force on the gas, I can write it as the surface integral of PdA minus PEAE is equal to m dot ue, and I can rearrange to make the surface integral the subject. So I end up with a term that I can use to substitute for PdA in the expression for FR. So in other words, I can rewrite the integral of PdA as PEAE plus m dot ue. So I can now substitute that into my expression for FR, the thrust on the rocket. So I've lost that awkward surface integral now, and I have simply terms in the mass flow rate, the true exhaust velocity, the exit plane area, and the exit plane and ambient pressure. And so with a trivial rearrangement, I end up with the expression for the thrust equation which we set out to derive.